Hello everybody, how are you doing? Hope everybody's doing very well. Today, ladies and gentlemen, we're going to look at Taylor's polynomial and convergences as we even prepare for the 2020 BC Calculus examination. We're going to look at a few free response questions that could possibly be on examination that involves Taylor polynomial, Brooke Taylor, his polynomial, and convergences that involves various series. Could be a p-series, an alternating series, or a limit comparison test or a direct comparison test. So we're going to look at that, okay? So we have a problem on the board, and this problem has 4 parts: A, B, C, and D. And so what we're going to do, we're going to answer each portion on the opposite side. Alright? So we're going to let this sequence A sub n equal -1 quantity to the power of n divided by n to the power of p minus 2. And we're going to let the sequence B subscript n equal -2 divided by n to the power of 6 minus p. So if we're given these two sequences, the first thing we want to do, we want to let p equal 2.5. Let's show that both of these series now, as n goes from 1 to infinity, that the series of an and the series of bn, let's show that they converge. And then we want to come back and we want to find all integer values of p such that the series an and the series bn both converge. What are those integer values that would cause convergence on both series? Okay? And then you want to come back and let p equal 4 and let f of x be a function with derivative of all orders at x equals 2 with f of 2 equaling -3. And where f to the power of n of 2 equals n factorial times the sequence an for all n greater than 1. Well, that's a lot. But what are we asked to do? Find Taylor's polynomial, third degree Taylor polynomial for f of x centered at x equals 2. So for part C, we're asked to find third degree or third order, or third degree, you can say order or degree, third degree Taylor polynomial for f of x, which is going to be centered at x equals 2. Alright. And then lastly, using the Taylor polynomial third order from the previous part, part C, well, in D we have to find what? The derivative of our third degree Taylor polynomial. Alright? And then when x equals 3, the series, this new series, C subscript n, which is not this sequence, nor this sequence, nor this series, nor that series, but we have another series here. Okay? Now this series is a p-series whose first 3 terms corresponds to the derivative of our Taylor polynomial. Okay? That's the derivative of our Taylor polynomial from part C. So the first 3 correspondents of this series correspond to the first 3 correspondents of the derivative of the Taylor polynomial here. Determine whether the series Cn, whether it converges or diverges when x equals 3. Very, very good questions, high-level thinking questions around the Taylor polynomial and around convergence, divergence, etc., etc. So let's go ahead and jump right into it, shall we? Okay, let's begin. Let's answer the first question, A. Alright, so let P be 0.25. Let's show that both of the sequences converge. Alright, well, let's do the first sequence. Sequence number 1. We go n equals 1 to infinity. Our first sequence is -1 to the n divided by n to the power of p minus 2. All right, so now let P equal 2.5. All right, so now we're going to have a sequence, or pardon me, a series rather, not a sequence. We're going to have a series such that we have -1 to the n divided by n to the p, which is 2.5, minus 2. Okay, we're getting there, which is going to give me a series where n equals 1 to infinity of -1 to the n over n to the 1/2. N to the 1/2 or n to the 0.5. Let me make this sequence a little bit better. N to the 1/2 or n to the 0.5. Here we go. N equals 1 all the way to infinity. Okay, so our sequence here, convergent or divergent? Well, let's see. First, you have to determine which test are you going to use to determine whether it's convergent or divergent. All right, and the first thing that I notice is this -1 to the power of n, which lets me know that it alternates. It alternates as n gets larger. Our series, it alternates. It goes from negative to positive, negative to positive, negative to positive, negative to positive. So we have an alternating series here. So let's look at the conditions for an alternating series. All right. If a series alternate, to be convergent, condition 1. Here we go. For alternating series test, that's what AST stands for, alternating series test. There are 3 conditions. Condition 1, well, a to the n has to be greater than 0. This means positive. Condition 2, a to the n plus 1 has to be less than a to the n. This means decreasing. Condition 3, the limit as n goes to infinity of a to the n has to equal 0. If those 3 conditions are true for any alternating series, then we have convergence. But all 3 must be true. And on the AP examination, you must show explicitly that all 3 are true. All right, let's go and investigate now. All right. So we know that AN, this sequence AN is 1 divided by n to the power of 1/2. Okay? That's what our AN is. It's 1 divided by n to the 1/2. Because when we're looking at AN, we do not include the -1 to the power of n. Okay? We don't include this right here in the AN. This is isolated. -1 to the n is isolated. So there we go. That's AN. All right? So condition 1. AN, which is 1 over n to the 1/2, is greater than 0 when n is greater than or equal to 1. In other words, 1 over n to the 1/2 is positive. It's positive. How do you know it's positive? Plug in 1 for n. I'm going to get 1 over 1 to the 1/2. 1 over 2 to the 1/2. 1 over 3 to the 1/2. 1 over 4 to the 1/2. So on and so forth. So as you can see, all of our values here are positive numbers. Alright, so condition 1 is true. So a to the n is greater than 0 and n is greater than or equal to 1. So we have positive numbers. So we're good. This one's a go. Condition number 2. Alright. Condition number 2 says it must be decreasing. You must show that the n plus 1 term is smaller than the n term. Or the n plus 2 term is smaller than the n plus 1 term. And so on and so forth. Alright. Now the best way, I believe, to indicate that, the sequence is decreasing, this is one way you can show it like that. Because look, we have 1, comma 1 over the square root of 2, comma 1 over the square root of 3, comma 1 over the square root of 4. Okay? And there's no doubt in my mind that 1 over the square root of 4 is smaller than 1 over the square root of 3. Okay? So yes, it is decreasing. These numbers are smaller as we go along in our sequence. The numbers get smaller. Or what you could do, and I think this is the more, use calculus. If I look at it like this, this is not using calculus. If you want to use calculus to show that it's decreasing, then approach it this way. Alright? If an equals 1 over n to the 1/2, if this is to be the case, if that, then a prime of n. What is our derivative of this right here? What's the derivative of 1 over n to the power of 1/2? Well, let's see here. That's going to give us negative 1/2 n to the negative 3/2, which equals negative 1 over 2 n to the power of 3/2. That's my derivative. Okay? And for every n value that you put in the derivative, right, the output is going to be less than 0. Negative 1 over 2 n to the 3/2 is always less than 0. Okay? And when the derivative is negative, comma, the function is decreasing. All right, there you go. There we go. So maybe not when. I want to write the word where. Where. That's better. Where the derivative is negative, the function is decreasing. Where this derivative is negative everywhere, no matter what value you put in for n, 1, 2, 3, 4, 5, we're going to get out a negative value. Whatever you put in, it's going to come out negative, which means we're strictly decreasing. So condition 2 is met. And then look at condition number 3. Check out the limit. Condition 3. The limit as n goes to infinity of an. An is 1 over n to the 1/2. This equals, well, 1 over infinity. 1 over a very large number is 0. Condition 3. We're good. It converges. Therefore, by the alternating series tests, our series of -1 to the n over n to the 1/2 converges. All right, and that takes care of that. So we know that this series here is convergent. All right, now let's chart out some space for our other series. Oh, wait a minute. How about our other series? Here we go. How about the other series? This one here, Bn. Convergent or divergent? Well, we're going to have our series n equals 1 to infinity. Let's go ahead and substitute, make our substitutions. We're going to have -2 over, go ahead and put 2.5 in for p. 6 minus 2.5. That's going to be n to the 6 minus 2.5. 6 minus 2.5, right? Which is going to equal n equals 1 up to infinity of -2 divided by n to the power of 3.5. All right? Ladies and gentlemen, this right here is not an alternating series because we don't go -1, +1, -1, +1. It's not alternating, but what you should notice is that it follows the order of a p-series. It is a p-series, okay? And we know a p-series is convergent, so recall, if you will, the p-series. P-series. So if you have a summation n equals 1 to infinity of 1 over n to the power of p, if p is greater than 1, then the series converge. So just look at the p, the exponential power. If it's greater than 1, we have convergence. What is our p in this case? Our p is 3.5. There you go. Therefore, by the p series test, summation n equals 1 to infinity of -2 over n to the power of 3.5 converges. All right, there you go. So A is answered. We have convergence for both series. One series we use the alternating and series test, and the other series we use the p-series test. Alternating series test and p-series test. When you looked at these sequences here, right, this should have been an indicator or a clue to let you know to use an alternating series test, because -1 to the power of n, that's what causes the sequence or the function to alternate between positive and negatives. So that should have been like a telltale sign. And here, -2 divided by p, -2 divided by n to the power of 6 minus p, that should give you an indication that that was going to be a p-series. So you should look for things like that early on. All right, so we're finished with part A. We have convergence for both. A is done. Let me erase the space. Erase the space. And now let's move into part B. All right, B. Find all integer values p such that an, that series, and series Bn converges. Find all integer values of p. All right, let's start with our an first. All right, so Let's start with an. And an is -1 to the n all over n to the p minus 2. Got it. Let's look at the series. The series n equals 1 to infinity. All right, of -1 to the n divided by n to the p minus 2. Got it. Notice, ladies and gentlemen, don't misunderstand this. This right here is what we call a sequence. And of course, this one over here is what we call the series. Okay? A sequence is just an order of terms. That's what a sequence is. It's an order of terms. It's an order of positive integer terms, right? A series, on the other hand, represents the sum of those terms when you add them all up. You can have an infinite sum or a finite sum, all right? So, let's take a look at the series here. Now, we want to find all the p-values. All right, so for our first problem that we did for part A, we used the alternating series test. Recall that? And recall that our a to the n was 1 over n to the 1/2. Okay? This right here is like a recall from part A. This is a recall from part A. And sometimes the way these AP questions are designed, you have to recall and use parts from the previous question to answer succeeding questions, right? All right. So we're using that from part A. Notice that the power of n is 1/2. Okay? It's 1/2. It's a positive number. So it goes without saying that we will get convergence if n, its power, is positive. It has to be positive. So we have to ensure that our power of n is positive. Okay? Like we have right here, 1/2. So our power of n, and in this case our power of n is p minus 2. So p minus 2 needs to be positive. All right? If p minus 2 is positive, then this means that p has to be greater than positive 2. And if that's to be the case, if p is bigger or larger or greater than positive 2, then we're going to have convergence here for this alternating series. For all those values in which p is greater than positive 2, we're going to have convergence. Because give me a number greater than positive 2. Okay, take 2.1. Okay? Well, if that was 2.1, we would have 2.1 minus 2, which is 0.1, and this alternating series still would converge by the alternating series test. It would not converge by the p-test, but this is not the p-test. It's an alternating series test because of this -1 to the power of n. So it would still be convergent. Point is, p has to be greater than 2. And the whole entire expression, p minus 2, has to be greater than 0. All right. That takes care of that one. Let's take a look at our other sequence. The other sequence is Bn. Bn is -2 divided by n to the 6 minus p. Okay, let's do a recall on this one. recall. What did we use in part A to determine whether or not Bn converged or not? We used the P-series test. We used the P-series test. All right, well, yep, we used the P-series test, and we said that our Bn I believe was like -2 over n to the 3.5. Okay? Now, recall that. And why did this converge? Why? It converged because converge because 3.5, which is the power of n, is greater than what? 1. There you go. So in order for this fellow to converge, the power has to be greater than 1. So let's go ahead and write our series. That's the sequence. Here's the series. The series as n equals 1 to infinity, right, of -2 over n to the power of 6 minus p. All right, well, we're going to have convergence here because of the P-series test when the power, and here's the power, when our power is bigger than 1. So set 6 minus p greater than 1, because that's when we're going to have convergence using the P-series test. Okay? Let's work it. So if I were to subtract 6 from both sides, I would get -p is greater than -5, and divide both sides by -1. Please do not forget the algebra, ladies and gentlemen. When you divide by a negative sign, the direction of the inequality has to shift. Okay? When you divide by a negative, what's going this way must turn and go that way now, when you divide by a negative. Or what's going this way, it must turn and now go this way. When you divide by a negative, okay? Or multiply by a negative. Same effect. Divide or multiply by a negative, you must change the direction of the inequality symbol. I like putting it like this. When you divide by a negative, or better yet, when something negative happens in your life, things change, doesn't it? Unfortunately, it does. So whenever you divide by a negative, something has to change. And that's what happens right here. So when we divide both sides by -1, -1, -1, please change the sign or the direction of the sign. So we're going to have p now is going to be less than 5. All right. There we go. Put them both together. All right. So I have p greater than 2, p less than 5. So I'm going to put the smallest number to the left. The smallest number is 2. The largest number to the right, 5, because that's the order in which we count from smallest to largest. Makes sense. Both of them have a p in common, so I'm going to put a p in the center. I noticed that up here, the inequality symbol is eating the 2, right? You see that? The 2 is being eaten. In other words, the p is being eaten. The mouth is being wide open and it's about to eat up. Give it some teeth in the tongue. See that? It's about to eat the p. So if the p is being eaten and the 2 is not, then I'm going to make the p be eaten right here. The p is still being eaten. And in this case right here, the 5 is being eaten. See that? Make the sign a little bit bigger. Put some teeth in it. Give it a tongue. See that? It's eating the 5. So make sure it continues to eat the 5. All right. So if you leave this as your answer and say there it is, that answer is incorrect. It's not the answer. Because in between -2 and 5, they're not only integers, there are some rational numbers. There are rational numbers in between, a lot of them. Billions and billions and billions and billions. Can't count them all. They're rational numbers. But that's not what the question said. The question says find all what? Here's the word, integers. Find all integer values, right? The integers are the natural numbers and their opposite counterparts. Those are the integers, the natural numbers, the natural way you were taught to count. You know, 1, 2, 3, 4, 5, 6. Those are natural numbers, okay? And so, what are the natural numbers or the integers between 2, not including 2, and 5, not including 5? Oh, here they are. P equals 3. And, no, not and. Or. You can't be both. Or. P equals 4. That's the answer right there. There you go. Those are the integer values that will cause both series, AN and the series BN, as n goes from 1 out into infinity. These are the values or the integers that will cause our series to converge. So that's your answer. Not this. No go. Right here. Here's our answer. Yay! Okay, very good. You doing all right? You breathing? Okay, that's question number, that's the first question we answered, A, and we answered letter B, okay? Now please notice, I'm being very deliberate about every step here, and that's how you want to be on this AP examination, because you have very few questions. You don't have questions 5, 6, and 4 and all of that. You just have maybe two questions and that's it. So whatever question they ask you, please, don't leave no stones unturned. Answer the question as thoroughly as you possibly can. All right? Okay. All right, so that's B. B is done. All right, let's move on to C. All right, C. What do we have here? P equals 4. Let f of x be a function with derivatives of all orders, and x equals 2, with f of 2 equaling 3, and where f to the power of n of 2 equals n factorial times a to the n for all n greater than or equal to 1. Find P3 of x, which is a third-degree polynomial, Taylor polynomial, for f of x, which is centered at x equals 2. Now, on the AP examination, you read a question like that, and you'll say, okay, I'm done. I'm done. There's two of us who was doing okay. We were doing pretty good with P series and alternating series and finding convergence and things like that. I was doing all right with that. But this right here, okay, next question. Just relax. Breathe. Take it easy. When you see a question of this magnitude that's rich in content, start with asking yourself the question, what do they want me to do? What are they asking me to do? Let's see. Here it is. They're asking you to find P3 of x, a third-degree Taylor polynomial for f of x centered at x equals 2. That's it. That's what they're asking you to do. And all this other stuff in here is going to help you to get there. But that's the key thing. Taylor's polynomial. So let's start with Taylor's polynomial. Let's start with that. Okay? Taylor's polynomial. Let's start there. All right, and let's call it P n of x. P n of x. Okay? I'm going to use P because that's the notation here. P n of x. It equals f of c. Let's start with that. F of c. And this c represents the center. C is the center. And they give you the value of the center somewhere here. Centered at x equals what? 2. See, they give you the value of the center. So just go easy. Breathe easy. Alright? Let's continue to work on Taylor's polynomial. Plus. Alright? Now, if you understand this, the next term is going to be pretty simple because it's going to be plus f, the derivative. First derivative, evaluated at c, times x minus c divided by, to the power of 1, divided by 1 factorial. Okay? So now we're building a case for Taylor's polynomial. And this pattern right here must continue. Okay? So trying to understand Taylor's polynomial in terms of sequence, what goes next in the series, what's next, and so on and so forth. Just look at this. You always start with f of c first. That's pretty obvious. Alright, Taylor's polynomial requires us to differentiate, take the derivative. We took our first derivative, we evaluated it at c. Now, notice this. First derivative to the power of 1, 1 factorial. First derivative, power of 1, 1 factorial. 1, 1, 1. The next term is going to be 2, 2, 2, 3, 3, 3, 4, 4, 4. It's a pattern. It's a pattern. It's a pattern. First derivative, power 1, 1 factorial. Let's do another one. Come on now. You have to see this pattern. Plus f double prime evaluated at c times x minus c squared, second derivative, all divided by 2 factorial. Okay, you starting to see how it goes? Let's go again. Plus f triple prime of c times x minus c quantity cubed all over 3 factorial. I can go on and on and on all the way to the nth term. I'm not going to do that because notice this. It said what? Find a third degree Taylor's polynomial. This means that you want to go all the way to a n equals 3. Here is n equals 1, n equals 2, n equals 3. And this one right here was n equals 0. Anything to the power of 0 is 1. N equals 0, n equal 1, n equal 2, n equal 3. I have a third degree Taylor polynomial. Here's the framework, here's the shell right there. If they wanted a 4th degree, you go out to the 4th derivative. 5th degree, the 5th derivative, so on and so forth. All right. All right, so we're doing okay. We're doing all right. So now, let's go back to what we have right here. All right, so we know that f n of 2. F n of 2 equals n factorial times a to the n. All right, this here is our sequence. They gave us the sequence. There it is. There's a to the n. Okay? So let's rewrite this. So I'm going to write it as f n 2 equals n factorial. And what is a n? All right, times -1 to the n over n to the p minus 2. Everybody good? Don't panic. Don't panic. All right, let's go a step further. They tell you what p equals. P is how much? 4. Let's rewrite it again. So we have f n of 2 equals n factorial times -1 to the n all over. And since p equals 4, 4 minus 2 is 2, n squared. All right. And so since we want a third degree polynomial, let's let n equal 1, 2, and 3. Because here's our n value. The first derivative, that means n is 1. The first derivative, that means n equals 1. Second derivative, n equals 2. Third derivative, n equals 3. Okay. Here we go. So let n equal 1. What are we going to have here? We're going to have f to the 1 of 2 equals 1 factorial times -1 to the 1 over 1 squared. Cool. Got it. What about f double prime of 2? All right. This means, hold on. Let me write this first. Now let n equal 2. So we have f double prime of 2, which equals 2 factorial times -1 squared, -1 squared over 2 squared. Okay? Now, bear in mind right here, I could have written it like this. I could have said f of 2 equals 2 factorial times -1 squared over 2 squared. I could have written it like that. I didn't have to write double prime. I could have just put the 2 there. All right? But we are talking about differentiation, so I'm going to leave it like this. Okay? Good, good, good. Now let n equal 3. So I'm going to have f triple prime of 2 equals 3 factorial times -1/2 cubed over 3 squared. All right. So if I want a third degree, that means differentiate 3 times. That's what this implies. Differentiate. Three times. If it were a fourth degree, 4 derivatives. Fifth degree, 5 derivatives. Second degree, 2 derivatives. Okay? The degree is indicative of how many times you have to differentiate. So I have a third degree, I have 3 derivatives here. Okay? And so what are these values? What does this equal? We need the values. Okay, here are our values now. Well, 1 factorial is 1, and 1 times negative 1 over 1 is just negative 1. So I'm going to have me a negative 1 right here. All right, negative 1. Which means, follow me now, this negative 1 is going to go in this position right here. Boom. That's negative 1. That f prime of c. Because c is 2. How you know c is 2? Because the center is 2. So f prime of 1, all of that is negative 1. What do we get here? Well, 2 factorial is 2. So I'm going to have 2 times 1 over 4, which is simply 1/2. All right, so 1/2 now is going to go right in this spot. And lastly, 3 factorial is 6 times. How do you know 3 factorial is 6? Because 3 factorial, that means 3 times 2 times 1. So 3 factorial equals 6. Okay? It's multiplying by the numbers decreasing or by the numbers increasing. Doesn't matter how you can decrease and multiply or increase and multiply. Same thing. Alright? And so negative 1 cubed is negative 1. All divided by 3 squared is 9. So that's going to equal negative 2/3. Alright. And negative 2/3 for my third derivative. This is going to go right in this location. I have my coefficients. Let's put it all together. All right. I think we're there. That's going to do it. So, P3 of x, which is a third degree polynomial. A third degree Taylor's polynomial is, oh, look at this. What is f of the center? Okay, what is that? That's the question. What is f of c, since c is the center? The center, they said, is 2. So what is f of 2? Do you see it up there? They give it to you? Here it is right here. It's located right here. They give you that. So they gave us this. They gave us this term. They gave us the algorithm for our differentiation. Everything was given to you. All you had to know how to do in essence was just understand what Taylor's polynomial is and the pattern of the polynomial. That's it. All right, let's put it all together now. So since f of c is negative 3, we're going to have negative 3. All right, plus, okay, what is f prime of c? Negative 1 times x minus, and what is c? The center is 2. All over 1 factorial. All right, plus, let's keep going. Plus, all right, f double prime of c, what was that? 1/2. Times x minus c, 2. And this is squared, all over 2 factorial. Plus, negative 2/3. Times x minus 2 cubed all over 3 factorial. There you go. There you go. Let's see if we can't like maybe simplify it down. Now bear in mind on the AP examination, if you stop right there and leave that as your answer, you would get full credit. You would get full credit for answering C correctly. Because that is the answer. That's it. We have found a third-degree Taylor polynomial centered at x equals 2. We have it right here. It is done. It is done. That's it. The only reason, so I would stop right there with part C. However, I do know this. When we look at the next question, D, it says using the Taylor polynomial of degree 3 that you found in part C. You see that? So to answer part D, I have to use this polynomial in part C, which is going to require me to simplify it. So probably when you start question D, simplify then. Don't simplify on part C, because if you simplify it on part C and make one mistake, they're deducting points. They're taking off points. So I think since I have my Taylor polynomial right here for part C, I think I'm going to stay right there. I'm not going nowhere with it. And I'm going to write it, put a box around it, and there you go. That's what it looks like. Now, let's go ahead and answer D. Let's answer D now. And I'm going to leave that here from part C to answer D. Put my line back. Alright, let's answer D. Using P3, third-degree polynomial of Taylor's that you found in part C, find P3 prime of x. Find the derivative of our Taylor series. We have to differentiate it. So if we want to differentiate this, we have to simplify it to differentiate it. Alright, so first, let me write it. So P3 of x. Let me just simplify this on out. So I'm going to have negative 3. I know 1 factorial is 1. I know a positive times a negative is a negative. Minus x minus 2. Alright, so far so good. Right here, plus. I know it's going to be positive. I know that 1/2, I know 2 factorial rather is 2. So I'm going to have 1/2 over 2, which is 1/4. So I'm going to have 1/4 of x minus 2 quantity squared. Okay, so far so good. Right here, what is 3 factorial? I'm going to have negative 2/3 over, what's 3 factorial? That's 6. Alright, which is going to equal negative 2 over 18. Because you see this division line right here? You put that line on top of this line. I call this the bump down. Just bump it down. You know, take this fraction right here and just bump it down a level. One level. Bump it down one level. And that becomes negative 2 over 3 times 6. If you take this and bump it down a level. Negative 2 over 3 times 6, which gives me negative 2 over 18, which is negative 1/9. Alright, so now I'm back up here. So I'm going to have a negative times a positive is negative, so it's going to be minus 1/9 times x minus 2 quantity cubed. Okay, now I'm ready to answer part D. So now I'm going to find my derivative now of this fellow. Let's find the derivative. So P3 prime of x. What's the derivative? just use good old chain rule when you find the derivative here. The derivative of -3 is 0. Don't have to write it. The derivative of x minus 2 is 1. There's a negative sign right here, so it's going to be -1. Now in this case right here, you have to use the chain rule. The derivative of the outer times the derivative of the inner. In this case, our outer is going to be 2 times 1/4, which is going to be a half, times x minus 2. Alright, and when you subtract 1 from 2, you get 1. But what's the derivative of the inner? X minus 2 is just 1, so we don't have to write that. Alright, minus the derivative here, again chain rule, 3 times 1/9 is going to be 1/3 times x minus 2, quantity squared. And then the derivative of the inner, x minus 2, is just 1. Alright, so this takes care of our first part. This takes care of find p prime of x. Alright? Alright, so now it says, so I can erase the bottom. Let me get rid of all this. This goes away. Goodbye. Now it reads, here we go, when x equal 3, that's critical. When x equal 3. So that means when x equals 3. I have an x right here, have an x right there, x right there. Okay. When x equals 3, let's read. The series n equals 1 to infinity of Cn. So now we're introducing a new series. It's not an, it's not bn, it's Cn. We have a new series now. Let's write the series. Our series as n equals 1 to infinity of Cn. We have a new series now. Alright, so this series is a p-series. We know what a p-series look like. That's 1 over n to the power of p, where p is greater than 1. So we know what a p-series look like. Got it. Whose first 3 terms correspond, that's the key word, correspond to the first 3 terms of the polynomial. Determine whether the series converges or diverges. Alright, come on a little bit closer. Watch this. The first 3 terms of the polynomial. Here's term 1. Here's term 2. Here's term 3. Well, in this case, you got to include the negative. Term 1, term 2, term 3. So these are the first 3 terms of P3 prime of x. Those are the first 3 terms of the derivative of our Taylor polynomial. Those first 3 terms correspond, right, to the first 3 terms of our new series. The new series is defined once you take 3 and plug it in for x. So this new series is defined by, here we go, -1 plus 1/2. Now you take this 3 and plug it in for x. What are we going to get? 1/2 of 1, or just a half, minus 1/3, take the 3 and plug it in for x. 3 in for x, 3 minus 1, 3 minus 2 is 1, and 1 squared is 1. So there you go. So what we're saying is, the first 3 terms in the polynomial that's differentiated corresponds to the first 3 terms in this series right here, Cn. Okay? So that's the correspondence. All right? So now let's talk about this series right here. Let's talk about the series. What do you notice about the series? Look at the signs. The signs. What do you notice about the signs? What sign is this? Uh-huh. And then what? Yes. And then what? Aha. Negative, positive, negative. Alternating series. Alternates. All right? So then I know that my sequence. No, I know that my series. N equals 1 to infinity of Cn. It can be defined as negative 1 to the n because it's alternating. This gives me the alternation piece. So now I've taken the alternation portion of this out. So if I take the alternation out, I'm going to have 1 plus 1/2 plus 1/3. And 1 is really 1 over what? 1. What's my numerator? 1 over. What's my denominator? If n equals 1, I go up from 1, 2, 3. That's just going to be n. Because when n is 1, that's 1. When n is 2, that's 2. When n is 3, that's 3. Okay? So there you have it. That's what Cn is. So I'm looking at the series as n equals 1 to infinity of negative 1 over n. That's what Cn is. Negative 1 over n. I have an alternating series. And the question is, does this alternating series, is it convergent or is it divergent? That's what they want to know. They want to know, does it converge or does it diverge when x equals 3? We've already used the 3. We used the 3 up here somewhere. We used the 3 already to get these values. So is this convergent or divergent? It's an alternating series. So in an alternating series, there are 3 conditions again. 3 of them. All right? So an is 1 over n. That's my an. Condition number 1. 1 over n is greater than 0. It is positive. And it's positive for all n greater than 1. Because my first term, if I put in 1, I'm going to get 1. Put in 2, I'm going to get a half. Put in 3, I'm going to get a third, fourth, the fifth, the fifth, seventh. So it's positive. It's greater than 0 for all integers n greater than or equal to 1. It's positive for all integers n greater than or equal to 1. That's number 1. 2 is a to the n plus 1 less than a to the n. Is it decreasing? Do we have a decrease in this case? Oh. Is it decreasing? Well, let's see. The best way to determine whether or not we're decreasing, again, take the derivative of 1 over n. Oh wait, I'm sorry. Let's not call it an. An is this one. Call it what it is. It's Cn. There you go. So this also should be a C. Not an A. Make it a C. Cn plus 1 and C to the n. Alright, let's see if it's decreasing. What's our derivative here? Alright, so C prime of n equals negative 1 over n squared, which is always less than 0. That's always negative. no matter what n values you put in there. And bear in mind, the n values starting at n equals 1, the same n value you put into the series is the same n value you put into the first derivative, or the same n value you put into the second derivative. The n values never change. Okay? The n values always stay the same. I don't care if it's for the series, for the sequence, first derivative, second derivative, third derivative, doesn't matter. N values stay the same. What is different though are our outputs. The outputs are different, but never the inputs. If this was in terms of x and y, the x values are the same. It doesn't matter whether it's the function, first derivative, second derivative. The x values are the x values. The inputs are the same. It's just the outputs that are different. Alright? So, no matter what n value you put in here, you're going to always have a negative output. Negative because of this negative sign right here. So condition number 2 is met. And condition 3, 1, 2, 3, we have the limit as n approaches infinity of 1 over n, which does equal 0. So all 3 conditions are met, which satisfies the alternating series test. So what can we say? Therefore, 3 dots. Boom, boom, boom. 3 dots in the shape of a triangle. That means therefore, series n equals 1 to infinity of Cn converges by the alternating series test. And that, ladies and gentlemen, is our answer. And we have just answered a free response question, a possible free response question on the BC Calculus test for 2020. All right? I have another one for you, so stay tuned. Here we go. Okay, now we are ready for our second possible AP Calculus BC question that could be on the AP test, or a question that could be framed of styles such as this one here. That's the one we just got finished doing. So let's take a look at this one now, okay? All right, so now we have our series AN, and this here should be 0. Let me change that to a 0. Because when we have factorials and powers, we like to start at n equals 0. Because we know that n to the power of 0 always equals 1. But that's 0. Like, for example, x plus 3 to the power n, if n is 0, we'll get a 1, right? So we can start with 0 in this case. So we have our series from 0 to infinity of a to the n, where an is 5 times the quantity x plus 3 to the power of n, divided by negative 6 to the power of n. All right. Let's go ahead and let's commence with answering our questions. Determine if the series converge or diverge when x equals 1. All right, here we go. So A, here's our series. The series is n equals 0 all the way up to infinity, and we have 5 times x plus 3 to the n, all divided by negative 6 to the power of n. Alright, so when x is 1, what happens? Convergence or divergence? Let's see. Put in 1 for x, and let's see what we're going to get. Alright, we're going to have the series now from n equals 0 to infinity. 1 is here now, and so 1 plus 3 is 4. So I'm going to have 5 times 4 to the n, all divided by negative 6 to the power of n, which equals, our series is going to equal, alright, so now I can rewrite this as 5 times negative 4 over 6 to the power of n. which equals n equals 0 to infinity of 5 times negative 2/3 to the power of n. This series is convergent. The series is convergent because of the geometric series test, which states if you have a series where n equals 0 to infinity of a1 times r to the n, if absolute value of r is less than 1, then the series converges. And I guess it's also good to know that the absolute value of r being less than 1 is the same as negative 1 less than r, which is less than positive 1. Okay, these two notations are two ways of expressing our inequality is the same thing. And in our case, our r happens to be negative 2/3. Okay? And negative 2/3, the absolute value of that is less than 1. So this negative 2/3 is in our interval somewhere right along in here somewhere. We get negative 2/3 right in there. Alright, so we are convergent by way of the geometric series test. This is a form that's geometric, as we express right here. Alright, so that takes care of A. A is done. Alright, B. Let's take a look or gander at B. B. What does B say? B says, let our series AN equal L, a limit, where L is a real number. Okay. Show that there is a value of X such that L equals 15. So what we have in essence here, we have a series that's converging to a limit L. Okay? So we have a series or a sum that's converging to a limit L. So let's write it out. Let's write it up for B. Here we go. So we have our series n equals 0 to infinity, and our series is 5 times the quantity of x plus 3 to the power of n divided by negative 6 to the n. Alright? And so let's go ahead. I have a power n numerator, power n denominator. Let's just write it as one term to the power of n. So this can be rewritten as n equals 0 all the way up to infinity. We have an infinite series here of 5 times x plus 3 over negative 6 to the n. Notice the form here, ladies and gentlemen. The form is still geometrical. Okay? This is a geometrical series in formation. Two separate words. In formation. It's formed like a geometric series. Okay? So we can consider 5 as our A1 and x plus 3 divided by negative 6 as R. The key thing here is for a infinite series to converge, for an infinite geometrical series, or geometric series, for an infinite geometric series to converge, one thing must be true. If a geometric series is going to converge, then it will always converge to A1 over 1 minus R. Okay? This is the infinite sum of a geometric series. This is the infinite sum, not of, let's go for. This is the infinite sum for a geometric series. There you go, right there. So what we're saying in essence is that this right here equals 15. So n equals 0 to infinity of 5 times x plus 3 divided by negative 6 to the n equals 15. And if that's to be the case, then the sum, the infinite geometric sum, this can be represented as A1 over 1 minus R. Bring down the equal sign and bring down the 15. So this has to equal 15. And let's go ahead and put the numbers in. Alright, so we know that A1 is 5 over 1 minus, or what is R? R is x plus 3 divided by negative 6. And that has to equal 15. Okay, then once you get to this step, the rest is Algebra 1, which students have to be very careful with, because that's where mistakes are made with the Algebra 1. Okay, so here we go. Let's see. So we have 5 divided by 1 minus negative x plus 3 over negative 6. That equals 15. Now here's how I'm going to attack this problem. Here's how I'm going to attack it. I note that a negative times a negative is a positive. That's step 1. Negative times a negative is a positive. So I have 5 divided by 1 plus x plus 3 over 6 equals 15. Then what I'm going to do, I'm going to multiply top and bottom right here, just times 1. 6 over 6. Just multiply times 1. 1 is what we call the multiplicative identity. Multiply by 1, nothing changes, right? Multiply by 1. So if I do that, I'm going to get 5 times 6, which is going to be 30, over. And then 6 times 1 is 6 plus. And then when I multiply 6 right here, the 6's cancel out. So I'm going to have x plus 3. And that equals 15. Alright? We're getting there. And so now I'm going to have 30 over 9 plus x equals 15. Right? And now I'm going to cross multiply. I'm going to take 9 plus x times 15. So I have 15 times 9 plus x equals 30. Equals 30. Alright, next thing I'm going to do, I'm going to divide left side and right side by 15. 15s cancel out. 15s cancel when you divide both sides by 15. So I'm left with 9 plus x equals 2. So it's obvious what x has to equal. So x has to equal -7. Because 9 minus 7 is 2. Alright? So there you go. So it converges to a limit L. Well, let's make sure it converges to L. Let's make sure -7 gives me something that's going to converge. That's going to converge to a limit. We have to check it and see. Okay? I'm not going to check it in terms of, I was going to see if it converges. Not actually what the sum is, even though I could do that. Let me see if it converges. We may take it all the way. Let's see. Alright, so x is -7. So here we go. If we plug it back in, so I have the sum. N goes to 0 to infinity. Alright, take -7, put it right in there. We're going to have 5 times -4 over -6 to the n, which equals the sum n equals 0 to infinity of 5 times, what is that, 2/3? Yep, 2/3 to the n. So we do know for sure that this converges. It converges. Why does it converge? Because our r is 2/3. So we're good. It converges. I mean, if you want to go and check the sum, well, we could do that very quickly. Let me see. So the sum of this series, so the sum of our infinite geometrical series is going to be, what is A15? Divided by 1 minus 2/3, which is going to be, which is going to give me the sum of this infinite series is 5 over 1/3, which equals 15. Bingo. Alright, we got it. Didn't ask for all of that, but then there you go. You can still check it and see what you got going on here. Alright, so A is done, B is done. C. Let D in. Now D in, that's a different sequence now. It's a different sequence here. It's not A in, now it's D in. Alright. Let D in equal A n divided by n plus 1. So we have the sequence A n divided by n plus 1. Find the interval of convergence and the radius of convergence. So let's go after the interval of convergence and the radius of convergence. And if you're ever asked to find the interval of convergence, radius of convergence, then what should come to mind, the test you want to use, is the ratio test. Okay? The ratio test, because you need the absolute values. The absolute value. So we have to use the ratio test in this case. Alright. So here we go. Interval of convergence and the radius of convergence. So, dn equals an, which is 5 times x plus 3 to the n over -6 to the n, and all this is divided by n plus 1. So that's what dn equals, which can be simplified down to 5 times x plus 3 to the n all over. Do the bump down, put this division line on top of this division line, take this expression and bump it down 1. So we have -6 to the n times n plus 1. Alright, that's dn. So let's take a look at the series as n equals 0 to infinity of our series 5 times x plus 3 to the n over negative 6 to the n times n plus 1. And on this we have to use the ratio test. So we have to use ratio. You have to use the ratio test to check for interval of convergence, and radius of convergence. We want to use the ratio test. And the ratio test says that the limit, if this is convergence, ratio test convergence. Ratio test convergence says that the limit as n goes to infinity of the absolute value of, in this case I'm going to use d to the n plus 1 divided by d to the n, it has to be less than 1. Okay. If it's greater than 1, we're divergent. If it's equal 1, it's inconclusive. If it's less than 1, we are convergent. Okay? So let's see what we get here. Let's give it a shot. So this is the convergence of the ratio test if this is true. Better yet, another way to write it is like this. If I just leave that there, here we go. Let's go less than 1, equal 1, greater than 1. All right. This one is convergent. This one is inconclusive. And this one is divergent. All depends on which one it is. So, in using the ratio test, if I'm less than 1, I converge. If I equal 1, I'm inconclusive. Inconclusive means the test fails. Find another test. If I'm greater than 1, then the series is divergent. Alright, so here we go. Let's go after it. Now, one thing I like to do, I don't like to express this in terms of division. Here's what I do. I look at the limit as n goes to infinity of d to the n plus 1, right, times 1 over d to the n, absolute value. I just go straight to the reciprocal when I multiply. I skip over this step pretty much and go straight to the reciprocal. Alright, so that's what we're going to do. We're going to go straight to the reciprocal. Alright, so in this case, we're going to have the limit as n goes to infinity of, first we need d to the n plus 1. Let's do that here. That's going to be 5 times x plus 3 to the n plus 1 over negative 6 to the n plus 1 times n plus 1 plus 1 multiplied by. So take now this expression and give me the reciprocal of it. The reciprocal times, all right, negative 6 to the n times n plus 1, all divided by 5 times x plus 3 to the n. Absolute value of all of this. Okay, now we're cooking. Now we got it. Boom. Good. All right. So now since we've written it out, let's go ahead now and do some algebraic manipulations. Let's expand some things here. All right. So next step. So I'm going to have the limit as n goes to infinity of 5. All right, here we go. 5 times x plus 3 to the n times x plus 3 to the power of 1. Because that's what this is. X plus 3 quantity to the n plus 1 is x plus 3 quantity to the n times x plus 3 quantity to the power of 1. All right, keep going. Times negative 6 to the n times n plus 1. All divided by. I'm going to line some things up here. Line it up. See, I got negative 6 to the n plus 1, so it's negative 6 to the n. I'm going to write it right here. Negative 6 to the n. And then I have negative 6 to the power of 1. And I'm going to write that off out the way somewhere. Negative 6 to the power of 1. Now I have n plus 2. I'm going to write that underneath here. N plus 2. Because that's what this is, n plus 2. Then I have 5. I'm going to put 5 right here. And then I have x plus 3 to the n. I'm going to write that right here. Put my absolute value bars back. The reason I do that, everything is now lined up so I can cancel out a little easier. It helps with the cancellation. So x plus 3 quantity to the n goes away. 5s go away. What else? Negative 6 to the n goes away. What else? What else? That's it. So I'm going to have the limit as n goes to infinity of x plus 3 times n plus 1 over negative 6 times n plus 2. Okay, good. Oh, absolute value. All right. Now what are we going to do? Well, please recall that the limit as n goes to infinity of absolute value of a times b equals the limit as n goes to infinity absolute value a times the limit as n goes to infinity absolute value b. You can multiply the products across limits. It's okay. So I'm going to split these two up. I'm going to split it. I'm going to erase some of this. I need more room. Let me erase that. Okay, so let's split it up now. So if I split it, I'm going to have the limit as n goes to infinity of, let's see, n plus 1 over n plus 2 absolute value times the limit as n goes to infinity of x plus 3 over negative 6. Take this, split it up because of this rule here. All right. So as n goes to positive infinity, all of these values right here are going to be positive. There's nothing negative there. So this is the limit as n goes to infinity of n plus 1 over n plus 2, and that limit is 1. So I'm going to have 1 times, now let's work on this. Okay? Well, we know the absolute value of negative 6 is positive 6, right? And as n goes to infinity, our x value here, well, what's going on with that? Don't know. I don't know. I do know this though. I know that this can be written, the limit as n goes to infinity of absolute value x plus 3 over 6. I do know I can write it that way. Why? Because the absolute value of x plus 3 over negative 6 equals the absolute value of negative 1 times the absolute value of x plus 3 divided by 6. And that's just positive 1. Alright, I can leave it like that. So it's going to be 1 times, this 1 times the limit as n goes to infinity of the absolute value of x plus 3 divided by 6. Alright, now, in order for this to be convergent, we said that it has to be less than 1 if it's going to converge. If our series right here is going to converge using the ratio test, it has to be less than 1. So let's go ahead and see what we get. When we have the absolute value of x plus 3 over 6 being actually less than 1. It's sort of like the geometric series, the sum, the infinite sum of a geometrical series. It's sort of shaped, structured the same way as that sum is. Okay, so we know that this argument right here, x plus 3 divided by 6, is sandwiched in between negative 1 and 1. So we're looking between negative 1 is less than x plus 3 over 6, which is less than 1. Multiply everything by 6. Negative 6 is less than x plus 3 is less than 1. Nope, 6. Multiply. Now subtract 3 from all sections. 3 from the center, 3 from the right, 3 from the left. So I'm going to have negative 9 is less than x, which is less than 3. And ladies and gentlemen, there you go. This right here is what we call a possible interval. It's the possible interval of convergence. It's not the actual interval of convergence, it's the possible interval of convergence. And the reason it's a possible interval of convergence and not the actual thing is, once you get these endpoints, which are exclusive, they're not inclusive, they are exclusive. Once you get those endpoints, you have to test the endpoints to see whether or not they are actually inclusive, if they are included in the interval. Because right now, these endpoints are not included in the interval. They are excluded. Well, let's see if they are included, okay? So we have to check it now. So let's check negative 9. Let's check negative 9. And see what's happening at negative 9. Alright. So now we have our check for negative 9, for x equaling negative 9. Plug it in. So I have my sum, n equals 0, out to infinity. Put a negative 9 right there. I'm going to have 5, negative 9, that's going to be negative 6 to the n over negative 6 to the n times n plus 1. Alright, well, the negative 6 to the n's cancel out. Well, what do we have now? So now we have the summation. N equals 0 to infinity of 5 over n plus 1. How about this series? Does this series converge or diverge? Okay? If it diverges, then we're good with 9. 9 should remain excluded. Then we're good. If this series converges, then we have to include, bracket, negative 9. Converges, you have to include it. Diverges, leave it open, the way it is right now. Another way to express this is like this. Open interval, negative 9, 3. Open interval. They're not included. So we're saying they diverge right now, but we don't know. It might converge. Let's see. So what about this series right here? Converge or diverge? Well, we know we're going to have some divergent series, harmonic series. You know, it's like the P series in a sense. Our power here on n is 1, so we know it's divergent. But if you had to show it's divergent, what would you do? Which test would you use? Which test would you use to show it's divergent? Here's what you look at. We have a rational argument here. We have a rational sequence. In other words, when I say rational, that means we have a fraction, a quotient. You know, a polynomial numerator, a polynomial denominator, if you will. It's rational. So whenever you have something rational, it's always good to use a comparison test. Be it the direct comparison test or the limit comparison test, right? And even to that end, I would highly recommend that you stay away from the direct comparison test in a sense. In other words, find a comparison to make, and then once you get your other sequence you want to compare it to, use the limit comparison test. That's what I would do. Find another sequence to compare it to, and instead of going all the way with the direct comparison test, I just use the limit comparison test. Why? Because either both sequences converge, either both series converge or both of them are going to diverge. It all depends. So, with that being said, here's what I'm going to do. I can compare this to the following. All right? I'm going to compare it to n equals 0 to infinity of 5 over n. Compare it to that. 5 over n. Comparison test. Direct comparison test. I'm going to compare this sequence, this series rather, to this series. Alright? Well, here we go. I do know this. I know that I'm going to call this an. If I let an equal 5 over n plus 1, and I let bn equal 5 over n, I know that they are both greater than 0. They're both a positive. That's number 1. That's condition 1. They're both positives. In condition number 2, I know that 5 over n plus 1 is less than or equal to 5 over n. I do know that. Alright? But here's how the direct comparison test fails. This is why I don't too much care for the direct comparison test. Right? If I compare these two, it's strictly less than. It's strictly less than. It's not equal, it's strictly less than. If I compare these two, what do I know about this right here? 5 over n. What do you know about that sequence? N equals 0. No, n can't equal 0. N equals 1 to infinity of 5 over n. Converge or diverge? If you say diverge, you are correct. What test tells you that it diverges? What test informs us that we have divergence here? What test? Very good. P-series test. Okay? So by P-series test, the series diverges. Because P is not greater than 1. This P equals 1. It has to be greater than 1. So I know this diverges. Here's the problem. By the direct comparison test, the larger sequence, which is here, this has to converge. If this converges, then it pulls the smaller one with it. If this converge, then this one here converges. If the larger converge, then the smaller converge. Well, guess what? This doesn't converge. It diverges. So this test, this direct comparison test, fails. The direct comparison test fails. Had 5 divided by n plus 1, had that diverged, then the larger one would diverge. So when the smaller one goes down further with divergence, it pulls the larger one down with it. Better yet, when the larger one converges and goes upward, it pulls the smaller one up with it. That's the direct comparison test. So this test fails. That's why I don't like to use it. Use the limit comparison test. There you go. All right. So by the limit comparison test says a couple things. One, the limit comparison test it says if an and bn, if they both are positive, right, then the limit as n goes to infinity of an over bn, if it's greater than 0, or the limit as n goes to infinity of bn divided by an, doesn't matter, greater than 0. Alright? If it's greater than 0, then what? Either both converge or diverge. Well, we already know that one of these is divergent. And so we do know that this series here is divergent. Okay? So the series as n equals 1 to infinity of 5 over n, this is divergent because of the p-series test. So we know something about one of these two. We know this one is divergent, right? So now let's just go ahead and utilize the limit comparison test. All right, so here we go. Let's utilize the limit. This right here, this is the limit comparison test. We're going to use this now. All right, so let's see here. Let's use this limit comparison test. And it doesn't matter which one we divide first, okay? So let's see. Since they're both positive, they're both greater than 0, so we're looking at the limit as n goes to infinity, right, of, let's say, 5 over n plus 1 divided by 5 over n, which equals the limit as n goes to infinity of 5 over n plus 1 times, multiplied by the reciprocal, n, oh, not 5, n over 5 equal. Well, the 5's cancel out, the 5's go, and so now I'm going to have the limit as n goes to infinity of n divided by n plus 1, which equals 1, which is greater than 0. So, therefore, we can conclude by the limit comparison test, right? We have either both series converging or both series diverging, okay? By the limit comparison test. Both series will converge or both series will diverge. Since we know that one of the series, since we know that this series here, which is from this sequence, since we know that this series is divergent, then that means that this other one here is also divergent. Okay? So at negative 9, we have divergence at negative 9. Okay? So at negative 9, we have divergence. All right. Now we have to check 3. You check -9, now check 3. Okay. Let's see what 3 is going to give us. So now we have to check for 3. We check for 9. Now let's check for 3. All right. So now we check for x being 3. Plug it in. Summation from 0 to infinity. All right. Now we're going to plug in 3. That's going to give us 5 times 6 to the n over -6 to the n plus 1. All right, let's manipulate it. Let's simplify it. Let's simplify it. So I can rewrite this now as the summation of n equals 0 to infinity of, okay, we're going to have, all right, now notice this. I have 6 to the n over -6 to the n, which can be written as 6 over -6 to the n, which is -1 to the n. Okay? So that's how I'm going to write this right here. This 6 to the n divided by -6 to the n. There you go. So that's -1 to the n. So I'm going to have the summation of -1 to the n times 5 all over n plus 1. Now I asked you, looking at this series, what test can you use? Looking at this series. Well, it's obvious what this is going to tell us right here. This tells us we should consider the alternating series test based on that -1 to the n. So we're going to attempt to use the alternating series test. Let's use the alternating series test. 3 conditions. For the alternating series test, we have 3 conditions. Condition 1, a to the n is positive. Condition 2, a to the n plus 1 is strictly less than a to the n. That means it's decreasing. And condition 3, the limit as n goes to infinity of a to the n equals 0. Okay? Let's check out our 3 conditions. All right? Well, we do know that a to the n, which is 5 over n plus 1, it is positive. That's condition 1. It's satisfied, and you know why. It's positive. There are no negative values here starting with 0. Plug in 0, you get 5. Plug in 1, you get 5 halves, so on and so forth. It's positive. Condition 2, it is decreasing. And you know why it's decreasing. You can take the derivative of it. The derivative of this is going to be negative. Okay? It's going to be negative for all values. It's decreasing. Or you can show that it's decreasing. You can do the derivative, which we've done before. Or in this case, you can just show the sequence is getting smaller. I mean, you know, plug in 0. Plug in 0, you get 5. Plug in 1, you get 5 halves. Plug in 2, you get 5 thirds. Plug in 3, you get 5 fourths. Plug in 4, you get 5 fives, or just 1. It's getting smaller. It is decreasing. Okay? So we see that. And then lastly, just check the limit. Check the limit. Let's see what the limit is doing. Look at the limit as n goes to infinity of 5 over n plus 1. And as you can see, as n gets increasingly large, so does n plus 1. And 5 divided by an increasingly large number goes to 0. All right, so with this value right here, here's the thing. We have convergence. We have convergence. So this converges. So since it converges, this 3 in our possible interval of convergence, it's not going to be an open interval or an exclusion, but the 3 now has to be inclusion. There you go. The 3 has to be inclusion, right? Because when you take the 3, plug it in, and you check it, you test it, we get convergence. So we have to include the 3. As you know, as terms of -9, when we check -9 and we plug -9 in, we did not get convergence. It was divergent, so we do not include it. So here we have the interval of convergence. Okay? So the actual interval of convergence the interval of convergence is open interval -9. Do not include it because -9 did not converge. Open interval -9, comma, 3 closed interval. There you go. That is our interval of convergence. All right, last part. Last part. Last question. Let f be a function that is twice differentiable at all x values if the first 3 terms of the sequence, or series rather, if the first 3 terms of the series are second degree Taylor polynomial for f of x centered at x equals -3, find f double prime of -3. Okay, our sequence. Our sequence is, it goes from n equal 0 to infinity of d of n. All right, so it's this right here. So that's our sequence. So let's put up our sequence then. So d. To infinity. All right, so it's an, which is there, which is 5 times x plus 3 to the power of n over -6 to the n, but it's multiplied by n plus 1. All right, so that's our sequence. Okay? And with our sequence, let's see here. Let's look at the first 3 terms. Let's look at the first 3 terms of the actual sequence. Let's look at the first 3 terms of the sequence. That's what it's saying to do. All right? So here we go. What's the first term here? Well, we have to let n equals 1. Let n equal 1. Okay? Well, no. We're starting at 0. Let n equal 0. All right, when n is 0, what do we get? We're going to get 5 times x plus 3 to the 0 over -6 to the 0 times 0 plus 1, which is going to give me 5 over 1, which is simply 5. All right, so this is going to equal 5. All right, How about when n equals 1? When n equals 1, what do we get? We get 5 times x plus 3 to the power of 1 over negative 6 to the 1 plus, no, times 2, which equals, that's going to be negative 12. 5 times x plus 3 all over negative 12. So I'm going to have minus 5 times x plus 3 all over 12. All right. How about now when n equals 2? What do we get? Well, that's going to be 5 times x plus 3 squared all over negative 6 squared times 2 plus 1. Alright, that's going to give me 5 times x plus 3 quantity squared divided by, what is that, 36? 36 times 3. Okay, that's going to be plus 5 times x plus 3 squared over 36 times 3. All right, so those are my first 3 terms. Term 1, term 2, term 3. All right, of the sequence, okay? But what we have to do, we have to look at the sequence, and we did, but we have to now compare it to a Taylor polynomial, right? Because the first 3 terms of the sequence are the what? Second degree Taylor polynomial for f of x. So now we need a Taylor's polynomial. No problem. Let's take a look at that. Taylor polynomial, and it's centered at what? Negative 3. Centered at negative 3. Taylor's polynomial. All right. And what's the degree on it? It is a second degree. Second degree. Okay, so I want P2 of x. I want a second degree Taylor's polynomial centered at negative 3. So first, without a doubt, this is going to equal first f of c. Okay? And c is the center, and the center is negative 3. So I'm going to just go ahead and put negative 3 in here. So first we have f of negative 3 plus. Now we take our first derivative. F prime of x plus 3 all over 1 factorial. Because there's a power 1. Remember now, first derivative, power 1, 1 factorial. 1, 1, 1. No problem. Plus, second derivative, f double prime of x plus 3 quantity squared. All divided by 2 factorial. Taylor's polynomial, and on and on and on and on. Okay? And so now what we have to do, if we want to find f double prime of negative 3. Oh, we left that out. That's important. Don't forget that. Yikes. I forgot to include the center. You must include the center. Plus f prime of negative 3 times x plus 3 to the power 1 over 1 factorial plus f double prime of negative 3 times x plus 3 squared, all divided by 2 factorial. All right. So if this is what we're looking for here, f double prime of negative 3, that's what we're going after, f double prime of negative 3. So what we have to do now, we have to equate the terms, right? Equate the terms. When I say equate the terms, that means you take this term and equate it with this one, right? Like f of negative 3 is equal to 5. They want you to equate the Taylor polynomial with the series. So if I equate the second degree Taylor polynomial with the series, you equate terms with terms. So you equate this one with this term. And then the second term in the polynomial with the second term of the series. And then obviously you must equate the third term. Here it is. The third term in the polynomial with the third term in the series here. And the reason you do this is because now you can find out what f double prime of negative 3 is. So what we have in essence, we have f double prime of negative 3 times x plus 3 quantity squared divided by 2 factorial equaling, there we go, 5 times x plus 3 squared over 36 times 3. And now all you have to do now is solve for f double prime of 3. Okay? And if we do that, I think I'm going to just cross multiply. So I have f double prime of 3, negative 3, times x plus 3 quantity squared. And this is going to be multiplied by 36 times 3. And that's going to equal cross multiply going the other way. 2 factorial is 2, and 2 times 5 is 10. That equals 10 times x plus 3 squared, right? And now what you do is you take all of this right here, divide both sides by x plus 3 squared times, well, what is that? What's 36 divided by 3? I'm just going to leave it like that. 36 times 3. Over here you have x plus 3 quantity squared times 36 times 3. Alright, 3 cancels, 36 cancels, x plus 3 quantity squared cancels, and all you're left with is f double prime of negative 3 equals. And there you go, that's what it equals. Notice this, that the x plus 3 quantity squares cancel out. 10 going to itself, 2 going to 10 5 times, 2 going to 36 18 times, and there you go. So it's going to equal 5 over 18 times 3 is 54, right? 54, okay, yep, 54, and there you go. That's it. And that is what f double prime centered at negative 3 is. Alright, and that's how you do it. So it's a matter of, finding, or having rather, a series, expanding the series, determining a Taylor's polynomial, and equating. The first question we did was kind of reverse. I had given you the Taylor's polynomial, and we had to go after the series. In this case, we looked at the series and had to go after the Taylor polynomial. So I hope both of these questions help, and we will do more as we go forward. Take care of yourself. Thanks for watching, and be sure to, whatever you do, always, always, always stay positive, okay? All right. Take care.